Hey everyone. In this Technology Insights episode of ITS Now, we are looking at inductive loop vehicle detection, which is probably the most important individual technology used in ITS applications because it's used so widely in applications as diverse as traffic signals, incident detection, vehicle classification, presence detection, etc., etc. I think it's probably worth stating that these are inductive rather than induction loops, which they're sometimes erroneously referred to as. The latter are actually used to wirelessly transfer energy. So within the ITS sphere, these are starting to be used for wirelessly charging electric vehicles. But no, you won't be able to charge your shiny new EV off the detection loops at a set of traffic signals. Anyway, I'm Alistair, and this is ITS Now. Inductive loops have been utilised extensively since the 1960s across a wide range of uses, including traffic signals, vehicle count sites, access control, and incident detection. Although newer technologies have been introduced over the years, loops are still considered to be highly reliable and are the standard against which other methods of detection are compared with. Many will be familiar with the outline of vehicle detection loops in our roads, a thin black line in the tarmac. Loops come in a variety of shapes and sizes depending on their use and the standards of the country being used in, but include rectangles, chevrons, circles, diamonds, and even butterflies. In the UK, the requirements for inductive loops are set out in the Manual of Contract Documents for Highway Works, or MCHW for short, in the Highway Construction Details G-Series drawings. The set of 32 drawings provide details of the various construction elements required for different inductive loop detection applications. Further technical guidance and links to other documents is given in MCH 1540, the specification for installation of detector loops. Also, the Federal Highway Administration Traffic Detector Handbook covers this. To install a loop, a slot is cut in the required shape and dimensions for the desired detection functionality. A connecting slot, called a cutback, to the edge of the carriageway is also required to allow the loop to be connected. It is essential to ensure that the slots are clear of debris before the cable is installed. There mustn't be any water in the slot when they are backfilled. This is normally done using a handheld leaf blower. A specialist insulated flexible wire, Hyperlan, is then wound around the loop slot 3 or 4 times, depending upon the size, required sensitivity, and the function of the loop. Then the ends, called the loop tails, are typically wired back through the cutback to a jointing chamber situated in the verge or footway. It's important to ensure that the loop tails are twisted so that the tails don't detect vehicles or other metallic objects passing in their vicinity. The slot is then backfilled to protect it from damage, often part filled with an epoxy resin, then finished with a bituminous hot pour sealant on top. Although inductive loops provide a reliable means of accurately detecting vehicles, their design and installation needs to be carried out carefully to ensure that the equipment provides a reliable level of service. An assessment of the carriageway condition should be carried out to ensure that it's good enough for loops to be installed into. Evidence of issues such as tram lining, where the road surface has been compacted by the wheel tracks of vehicles, differential subsidence, heave or cracking, and breakup of the wearing course may result in a reassessment of the method of detection to be used, or for the carriageway to be resurfaced. It is worth noting that in some locations, including the US, some loops are pre-formed and installed in the road base before the wearing course, the top surface of tarmac, is rolled out over them. Stick-down loops are also used in situations like concrete multi-story car parks structures, where it isn't possible to slot cut the loops into the carriageway surface. However, these wouldn't stand up to enough wear for highway applications. The wire in the pit is jointed to a feeder cable. This was traditionally done using a chemical or heat shrink joint, but increasingly this is now done using a lightweight bottle joint. The feeder cable is fed through the duct system to the TSC or equipment cabinet, where it is connected to a detector pack. The feeder cables contain twisted pairs of cable, usually in an earth steel wire armored sheath, to provide both mechanical protection and to minimize electrical interference. Once switched on, the loop coil emits an inductive field which is disrupted when a metal object passes through it, such as a car or a lorry. The detector pack processes information regarding the changes in the signal it receives, and when an anomaly is detected, an output is generated to indicate the presence of a vehicle. The process involved is essentially similar to that used by a handheld metal detector, but in this case the sensor is buried in the ground and is affected by metal objects passing overhead. Although this technology has been widespread since the 1960s, it is still seen as the baseline that other detection technologies are measured against. To show you how this works, I've set up an example to demonstrate an example of a single loop.
So what we've got here is this loop of wire going round. I've set them round 4 cones, so it's reasonably taut, and this is a 3-flex ordinary electrical wire, so it isn't what you'd use in an actual installation. That would use something called Hyperlon wire, which is quite a thin black flexible wire, which would actually be laid into the slot. Most loops use 3 turns in that. So that's the loop coil itself. And then here you see the loop tail, this black and white cable, which is twisted. And this would normally go back into a joint in the verge, in a chamber in the verge, and then taken back using a loop feeder cable back into the controller cabinet or into a roadside cabinet of some sort with a detector pack in. So here we've got 2 4-channel detector packs. We're using this one, and you can see the lights on here, which has been switched on so that you can see them. So we're only using 1 channel at the moment, so this loop is actually coming into channel 1 here, and we'll see that going in a minute. But these are standard types of formats that are used for detector cards. So the interface on the back then going to traffic signal controller or account side or whatever, those bit patterns are all defined, so you can actually use different brands of detector packs in without any hassle. So here I've just got this on a power supply, but normally, as I say, this would all be within a roadside cabinet. So anyway, so we've got the loop tail. So what I thought I'd do here, got electromagnetic detector, which seems to have just faulted. Is that right? Here we go. Right, so here you can see how those lights are continuously monitoring. So that shows that there's an electromagnetic field here that is detecting. If we go and do the same thing with the loop tails, you can see that doesn't happen, and that's because of the twist on here. So that's why it's so important that the tails, from the very point where the corner of the loop is, that they're twisted all the way back in the cutback slot, all the way into the chamber to where they're actually jointed, because otherwise they'll pick up either vehicles going over the cutback or just random noise, which means that the whole installation would be no good. Basically, it would be unreliable. It would be double counting, adding extra vehicles for other lanes, etc. Anyway, so how does this work? So it's basically like a metal detector, only instead of looking for metal in the ground, we're looking for a car basically going over the top of this. So what I do, you can see that LED coming on as I push this through this field, and this extra light comes on. You can see, probably hear it as well, it's clicking on and off, and that's all there is to it. This is more or less the size of ordinary chevron loop. I've just set it out square because it was easier here, but obviously the shapes differ. You can get round ones and different sizes and shapes, etc. But that's the basic way in which these things work.
Next, we're going to look at an installation of motorway incident detection loops to show you how these are typically installed. You will see that this consists of 2 loops in each lane with cutbacks to the verge to allow these to be terminated. The installation of an inductive loop will normally require the lanes either side of where a loop is being installed to be closed. This is because the footprint of a loop stretches across most of the affected lane, and the slot cutting machines are also quite wide as well. So additional clearance is required to protect the installation operative whilst undertaking these tasks. On multi-lane installations, like the example we're going to show you, the cutbacks from the outer lanes also cross the inner lanes to reach the termination point in a chamber in the verge. So it isn't really practical or safe to try to maintain a live lane. So this example was done under a full closure. It can therefore be difficult to get an opportunity to replace loops. So regardless of use, these are often done at night when traffic volumes are lighter, but adding considerably to the cost. As we saw in the video, testing of loops is essential. The generic test requirements for loops is given in drawing G6, although many highway authorities have their own versions of this. Tests are normally undertaken at the end of the loop tails before they are terminated to the feeder cable. Then once this is done, they're also tested at the far end of the feeder cable in the equipment cabinet where the detector cards are housed. The electrical tests include measuring the resistance and inductance of the loop, then loop and feeder cable, followed by a series of resistance measurements to earth. The length of the loop tails and feeder cable are also measured to ensure that the results of the electrical testing is accurate. Measurements of the distance between the leading and trailing edge of the loop, and if installed as a pair of loops in a lane, the distance between the two loops may also be required to ensure that the system will interpret parameters such as vehicle speed and vehicle length correctly. The actual location of the loop may also need to be measured. Mover loops, for example, it's important to record the distance to the traffic signal stop line because the data set needs to know what this is to accurately time the signal phases. The from stop line distance, referred to as FSL for short, is measured from the near side leading edge corner of the loop, not the distance between the nearest edge of the loop to the stop line. Once installed, terminated and operating, the setup of the detector cards needs to reflect the requirements of the particular use. Different manufacturers have varying means to set these, but typically on a 4-channel card, each channel is set to minimize crosstalk between adjacent channels, and the sensitivity of each input is adjusted to minimize false triggers, whilst also allowing more difficult to detect vehicles such as bicycles to be detected reliably if needed. It is also essential to ensure that the loops are terminated into the correct channel inputs of the detector cards. If there's a road or lane closure, it might be possible to drive a vehicle over each loop in turn to verify this. But if the site is open to traffic, it is much harder to achieve this accurately. In this situation, it's necessary to have a spotter located adjacent to the loop being verified, and using a hands-free mobile phone or radio, tell the engineer at the cabinet when vehicles are actually passing over the loop. The engineer will then need to ensure that the operation they are seeing on the detector card panel matches the information the spotter is calling out to them. If it doesn't, they will need to investigate what is going on.
Please remember to click on the like and subscribe to keep updated on ITS Now.
At the corners of loops, a small intersecting slot called a crosscut, or a 45 in the US, is often used to reduce the strain on the loop cable by removing the sharp internal corner that could possibly damage the Hyperlon cable. It's important that the crosscut is accurately located at the junction point of the two side cuts and doesn't leave a small area of tarmac between them. These are referred to as floaters because over time they have a tendency for these to break away and cause a pothole to form at the corner point of the loop. One of the weakest parts of a loop installation is the transition point where the loop tails go from the carriageway surface to the verge or footway. It has been common in the past to take the loop tails back to the jointing pit by cutting them directly through the curb or into the verge, but this can leave the tails vulnerable to damage and weaken the curbing. The design should therefore incorporate a reliable means of making the transition from the carriageway into the verge or footway, such as using a carriageway loop tail box. These are used by cutting the loop tails directly into the ductile iron box into the carriageway surface. The tails are then routed through a flexible conduit in the bottom of the box, which connects to a pit in the verge by running it under the curb. The tails are then jointed in the pit to the loop feeder cable. Whilst loops are being slot cut, it is essential to ensure that the slots are cut to the required depth. Contractors may try to cut these too shallow in order to minimize the time required. A number of issues can occur if the slots are not deep enough that would lead to premature failure. The backfill is more likely to come away, exposing the loop cables, which will result in the cable being worn or broken. The loops will be destroyed by planing out during resurfacing works. During the life of a loop installation, damage to the road surface can result in the loop not working. Damage tends to be caused by two issues. The first are utility companies who are notorious for trenching through loops whilst carrying out works. The second is caused by deterioration of the carriageway. Breakup of the surface will result in the loops becoming exposed and damaged, and tramlining, differential compaction, can result in the loop wire becoming stretched and subsequently breaking. Installed properly, inductive loops will provide a reliable, long-lasting and effective means of detecting vehicular traffic. They don't suffer from the obscuration or climatic issues that affect most forms of verge-mounted above-ground detection. I think this episode shows the huge array of information that relates to an individual area such as inductive loops. In reality, there's probably enough content to make a whole series on this subject alone. If you did find this useful, have a look at our books in the publication page of itsnow.org. Big thank you to Crown Highways for their assistance with making this episode. If you'd like to be involved in a future Technology Insight episode, please feel free to get in contact. Could I ask you to please subscribe to our channel? This will really help us to bring you further videos about ITS. Thank you to everyone who has so far. Thanks for watching. See you next time.